Hello, scholars. Once again, we have a lot of material to cover in a very short amount of time. So let's hop to it. Today we're looking at Chapter 2, Big Concept number 2, and we're actually talking about polynomial functions. So our objective, I am learning to graph polynomial functions. Now, one thing that you probably never realized is a polynomial function is the sum or difference of two or more monomial functions, monomial meaning one. The leading coefficient of a polynomial function is the coefficient of the variable with the greatest exponent. I'm going to say that again, the greatest. Now, polynomial functions are defined and continuous for all real numbers. So there's no discontinuity, and they have smooth, rounded curves. So here is an excellent example of a polynomial function. We are continuous. We have smooth, rounded curves. All right, so now I want you to recall from a previous lesson, graphs of even degree resemble the graph of f of x equals x squared, while graphs of an odd degree resemble the graph of f of x equals x cubed. All right, so when we take a look at this function, we have x minus 2 to the 5th power, which means it's going to have that cubic shape, except that it'll be a little wider towards that middle part. So I know that I'm going to be somewhere around this area probably. And I know that I'm going to be wider before going up and wider before going down. Very rough graph. It is what we call a rough sketch. All right, and when we take a look at x to the 4th plus 1, we'll go up to our 1. It has that even exponent, however, that is a negative a, so I know I'm going to be going down, and I'm going to be actually a little wider. It's going to be that wider U shape before going down. All right, so when I take a look at Desmos, I see there is my rough graph of x minus 2 to the 5th. It's rough, but it is very similar in shape. And there's my rough graph of negative x to the 4th plus 1. Once again, rough shape. We got the overall idea. All right, so now we're actually going to talk about what we call the leading term test. And this is a very important concept. Once again, it's going to help save so much time when it comes to sketching graphs. So basically, you're going to use the power and the coefficient to determine the polynomial's end behavior. We kind of talked about that a little bit in our last lesson, but now we actually have a name for it, the leading term test. So here we have the end behavior of any non-constant polynomial function, such as this all big long thing, can be described in one of the following 4 ways. Now, the only term that matters is this first one right here. And I'll write it down again, an x to the n. So it says if n is odd and a sub n is positive, our end behavior looks something like this. So n is odd. It has that cubic shape. Now, it doesn't really matter how high our maxima are or how low our minima are. We just know that it's going to have that cubic shape. So the limit of f of x as x approaches negative infinity is negative infinity, and the limit of f of x as x approaches positive infinity is positive infinity. So if n is odd and a is negative, we do that reflection like we normally would. So it says the limit of f of x as x approaches negative infinity is positive infinity, and the limit of x as x approaches infinity is negative infinity. Now, once again, this is a concept that you want to write down, take notes, commit it to your memory. It'll save you so much time. So now, once again, we have a to the n, x to the n. If n is even, remember that quadratic shape, that U shape, and a sub n is positive, we're going to have that smiley. Our n's are going to be smiling. So that says the limit of f of x as x approaches negative infinity is positive infinity, and the limit of f of x as x approaches positive infinity is positive infinity. And then conversely, if a sub n is negative, we're going in the negative direction for our limits. So let's take a look at some examples. So here we have example 1. Our a is 3, which is positive, and our n is 4. Now remember, a and n both refer to the leading coefficient, the one with the highest power. Our powers are 4, 2, and this has a power of 0. So yes, this right here is our leading coefficient, or leading term. So because we know a is positive and n is even, we can automatically use the fact that the limit of f of x as x approaches positive infinity equals positive infinity, and the limit of f of x as x approaches negative infinity is still going to be positive infinity. That is because it's that smiley face shape. It doesn't matter what's happening in the middle. Our ends are going to always be the same. It has that positive. That means I'm going to have it going into positive infinity in both directions. All right, so here we have negative 3x squared minus 2x to the 7th plus 4x to the 4th. Which one is our leading term? If you said negative 2x to the 7th, you would be right. So in this case, a is negative 2. So no matter what, I know I'm going to be switching my direction, and n is 7. So it's that cubic shape, but it is reflected across that y-axis instead. So it's going to have that basic shape. So that says the limit of f of x as x approaches positive infinity equals negative infinity, and the limit of f of x as x approaches negative infinity is positive infinity. You have to commit these shapes to memory. You need to know what a cubic looks like. You need to know what it looks like if it's reflected across the y-axis. You need to know what a quadratic looks like. You need to know what it looks like if it's reflected across the x-axis. All right, so now looking at this one here is our leading term. We have an a of 1, which is positive, and we have an n of 3, which is odd. So now I know it's going to be that cubic shape again, but it's in the correct direction. So the limit of f of x as x approaches positive infinity equals that positive infinity, and the limit of f of x as x approaches that negative infinity is going to be negative infinity. So it's all about committing those generalized shapes to your brain and using these rules to help do a quick and dirty end behavior analysis. All right, so now let's take a look at the power of a polynomial function. So the power also indicates the number of potential x-intercepts. Here's the key word, potential. For instance, a cubic function will have at most 3 x-intercepts, while a quartic function, to the 4th power, will have at most 4 x-intercepts. Turning points, and I referenced this in class a couple weeks ago, indicate where the graph of the function changes from increasing or decreasing. It also is where the maxima and minima occur at those turning points. So turning points can be found by taking the highest exponent or the power of that polynomial and subtracting by 1. So let's look at this example right here. So we have 3x to the 6th minus 10x to the 4th minus 15x squared. The number of zeros refers to the power of the exponent. So at most, we're going to have 6 potential zeros. Our turning points are 5. You take this number and subtract 1. And that's how you get your turning points. Now your end behavior. A is positive. N is even. So that means I'm going to have that smiley face shape, which means the limit of f of x as x approaches positive infinity equals positive infinity. And the limit of f of x as x approaches negative infinity is still going to be that positive infinity. All right, let's take a look at the next example. State the number of possible zeros and turning points. Determine the real zeros by factoring. So we're doing an extra little bit right here. The number of real zeros by factoring. So when we take a look, we have x cubed minus 5x squared plus 6x. Our highest exponent is 3. So there are 3 possible zeros. Turning points is the highest number, minus 1. So we have 2 possible turning points. Our a of our leading term is 1. Our n is odd. So we have positive. So it's going to be that cubic shape. So that says the limit of f of x as x approaches positive infinity gets me positive infinity, while the limit of f of x as x approaches negative infinity gets me negative infinity. Now it says to go ahead and factor. So let's go, we're going to do this right up here at the top. We have x cubed minus 5x squared plus 6x. The first thing I know with factoring is that I'm going to have to set it equal to 0. I also know we have a GCF because we have x cubed, x squared, and x. So if I pull out an x, I'm left with x squared minus 5x plus 6. This is a quadratic function with a leading coefficient of 1. So I need the factors of 6. That'll get me negative 5. So that leads me to x minus 3, x minus 2 equals 0. Now I'm going to set each of these pieces equal to 0. So x equals 0, x minus 3 equals 0, and x minus 2 equals 0. So when I solve these, I know x equals 0, but then I have x equals 3 and x equals 2. From our previous notes, we know that zeros are my x-intercepts. So I have x-intercepts at 0, at 3, and at 2. All right, and then I can start filling in my end behaviors. So this says as x approaches positive infinity, y approaches positive infinity. So that means this is going to go somewhere like this. This one says as x approaches negative infinity, y approaches negative infinity. And so now I just need to figure out, well, I have 2 turning points. That means I'm going to have to turn twice. So that is just a guess. This middle part right now is just a guess. We will get closer to what it looks like here in a moment, but I'm just scaffolding it up. I'm giving you baby steps so we can get it all together. All right. So now, here's a big thing right here. If a factor occurs more than once, it is called a repeated zero. Now, repeated zeros talk about multiplicity. So when the 0 occurs an even number of times, the graph will touch the x-axis. However, if the 0 occurs at an odd number of times, the graph will cross the x-axis. This is multiplicity. Well, Miss Younger, what the heck do you mean by multiplicity? Well, I'm going to show you an example so you have a better grasp of what I'm talking about. So once again, let's take a look. Distinct real zeros. I have a 4, so I have 4 possible distinct zeros. Turning points is the number of zeros minus 1, so I have 3. And then my end behavior. A is negative, N is positive. So that means I'm going to have the frowny face shape, which means my limit of f of x as x approaches positive infinity equals negative infinity. And so the limit of f of x as x approaches negative infinity is also negative infinity. So now let's go ahead and factor. We have negative x to the 4th minus x cubed plus 2x squared. I personally don't like negatives if I can have them as leading coefficients. So that is what I'm going to factor out. I'm going to factor out a negative x squared. When I do that, I'm left with a positive x squared, a positive x, and a negative 2. So let's go ahead and factor this. We have negative x squared. I need the factors of negative 2. That'll give me a positive 1, which is x plus 2, x minus 1. Set each piece equal to 0. So negative x squared equals 0, x plus 2 equals 0, and x minus 1 equals 0. So x squared equals 0, x equals negative 2, and x equals 1. Now, if you take a look, this is x times x, which means x equals 0 twice. That is what we call a multiplicity of 2. So when we plot negative 2, 0, and 1, we'll take a look at several different things. First, we know that it is the frowny face, so I know that it's going to go off in the downward direction. But now, I know a little bit more about this middle part. I know that when I come up to 1, because it is an odd multiplicity, a multiplicity of 1, it is going to go through my axis. And I know when I come to 0, it has a multiplicity of 2, so it touches it. So I just bounce right back up. And this multiplicity at negative 2 is 1 as well, which means it's going to go through. So now I'm getting a little bit more detail into my graph. So the key here, multiplicity, odd multiplicity, crosses, even multiplicity, touches. And when I say crosses and touches, I'm talking about the x-axis. All right. So now we have one last example. We're going to try and take as much as we have learned and apply it to this one example. So it says, for f of x equals x times the quantity 2x plus 3 times the quantity x minus 1 squared, apply the leading terms test. So A, leading terms test. I'm going to take each piece, each leading coefficient of each piece. So x times 2x times x squared. That gets me 2x to the 4th, which means my A is positive, my N is even. So we know it's going to be that smiley graph. All right, so now zeros. We have x times 2x plus 3 times x minus 1 squared. I know that I'm going to have my highest degree is 4, which means my turning points are 3. So when I go to these zeros, I have x equals 0. I have 2x plus 3 equals 0. And I have x minus 1 equals 0. Now notice, this has a multiplicity of 1. This has a multiplicity of 1. But this has a multiplicity of 2. Which means that this is going to cross. This is going to cross. And this is going to touch. the x-axis. So when I isolate x here, I get -3/2. When I isolate x here, I get 1. So those are my zeros. Let's go ahead and add them to my graph. I have an x at 0, at -3/2, which is -1.5, so we'll put it right here, and at 1, which is right around here. All right, I know my end behaviors. Because of the leading term test. The limit of f of x as x approaches positive infinity is positive infinity, and the limit of f of x as x approaches negative infinity is positive infinity. So I know that these are both going to go somewhere in that positive direction. I now know that I'm going to go through the point -3/2. I'm going to go through the point 0, and I'm only going to touch this point at 1. But how far or how tall or how low are my maxima or minima? To determine that, we need to add some extra points, which is part C. Find a few more points. So here we have between 0 and -3/2. Well, between 0 and -3/2 is -1. So if we have x equals -1, what does our y equal? Well, so we get -1 times 2 times -1 plus 3 times -1 minus 1 squared. So when I put that into my handy dandy calculator, I get -4. So I know I have another point at -1, -4. So I'm going to go here, here's -1, here's -4. Okay, so I'm going to go down pretty low. Now, between 0 and 1, let's choose 1/2. So if x equals 1/2, we have 0.5 times 2 times 0.5 plus 3 times 0.5 minus 1 squared. And when I put that into my calculator, I get 0.5. So now I have a 0.5 comma 0.5 point. So 1/2, 1/2. So I'm looking right around this mark. So now I have a better idea of how this shape is going to go. I go through, I touch, and boom, we're done. All right, so I know that was a lot, and here's the thing. This does take practice. You really need to memorize and commit to memory the different end behaviors for even and odd functions, how the degrees and turning points all relate, especially with the zeros and the crossing and the touching. Make sure you're applying it. Make sure you're taking excellent notes. If you have questions, please let me know. Y'all have a good day.